Today I want to talk to you about Xen in embedded across multiple verticals, and I'm going to talk a lot about automotive, as you see from the first slide. But in reality, many of the comments I'm going to make and the architecture I'm going to show you apply also to avionics, for instance, and also industrial. And the first thing I want to talk to you about is there isn't just one. If we take automotive as an example, there isn't one vehicle, one car is not one target. It's multiple targets. So a car has many systems, and of different degree of complexity. And at two extremes here in the example, you have on the left side the in-vehicle infotainment, which from a virtualization perspective certainly looks more complex, has a higher number of VMs. It has a lot of device sharing, Virtio or PV drivers. There is Android running there. It's definitely richer. And on the completely opposite end of the spectrum, you have the Vision Hub, which is the obstacle detection system, the one that is processing the camera feed and then detecting that you are running into someone else. This part is not necessarily less complex overall, but from a virtualization perspective, is less complex because there is no device sharing. Everything is directly assigned to VMs, and each system accesses devices directly. There is no PV drivers. There is no Virtio. So it's definitely lower complexity. Real time, though, is a factor here, right? Because the time response over that camera feed and detection of the obstacle in front of your car is very important. So it needs to be extremely low latency. While infotainment, you might have audio glitches, but that in terms of latency, we are talking milliseconds, while in the Vision Hub, you're talking microseconds or nanoseconds. So, but the point of this slide is to tell you is a spectrum. So it's not one target, it's multiple target, and complexity varies. And the key message here is Xen supports all of the spectrum, from the most complex to the least complex. And I'm going to show you today how we cover the whole spectrum. And this is an example of a system that, an AMD system with both AMD x86 as well as ARM with both IVI and the Vision Hub for the same vehicle. So you not only have one Xen running on AMD x86 or ARM, we have multiple Xen running. You have at least two, one on the x86 side for the IVI system, one for the Vision Hub on the ARM system, and as I'm going to go over in a few slides, you have actually more Xen running on the ARM system because the ARM system itself is heterogeneous. So you have Cortex-A that are the more powerful ARM processors, but you also have Cortex-Rs, which are the smaller microcontrollers, and Xen runs on both sides, both on the Cortex-As and the Cortex-Rs. All right, so let's start with the simplest first. Simplest is also sometimes called static partitioning because you're just caring about dividing your board into multiple domains and running different systems in the different domains. So there is no device sharing typically in this scenario. And one interesting feature here that's useful is CPU pool because you might want to have certain CPUs with a null scheduler, certain other CPU with a credit scheduler. So this is kind of useful. But in a pure static partitioning scenario, you will only use a null scheduler, right? Pure static partitioning means everything is directly assigned, including CPUs. So in the simplest of cases, and this is very common, industrial too, so we have lots of customers using this kind of deployment, everything is simple, there is no overcommit. And the other feature that by now all of you have heard of is DOM zero-less, and just to quickly recap, what it does is it boots things in parallel. So you load the domains at boot time, and then you boot them in parallel directly from Xen. And it's not just about speeding up the boot time in DOM zero-less, it's also about privileges, because the domain construction is now done by Xen, then you don't really need DOM zero anymore. I mean, it's useful if you want to have it around. There is nothing preventing you from having it. And if you have DOM0 around, you can do monitoring. You could do other things. But the point is, it's not required. And you can imagine that in the simplest scenario where you are dividing your board into two environments and running Linux on one and an RTOS on the other, like Zephyr, this is a very good match. And the null scheduler is a very good match. Which brings me to this slide, which kind of summarizes how Xen for static partitioning is configured. So first of all, everything is defined statically beforehand. So that's another thing, key aspect of DOM0less. It allows you to define all of the VMs that you have running before even turning on your target board. You already defined the VMs are going to run, where they're going to run, the devices that they're going to access. Everything is predefined and static. The number of vCPU for each VM, vCPU to physical CPU assignment, device assignment. Memory allocations too. Now, what about DOM0? So take away DOM0. Now you have no privileged VMs running. You have no hypercalls. I know that for, especially for a long time on x86, hypercalls really were the key. But here, on a runtime system with static partitioning, you only have running on ARM, at least, the interrupt controller driver plus the virtual corresponding part of it, UART and timer, and that's it. Because all the resources are directly assigned. Therefore, there is actually no hypercall being used. So the footprint of Xen at runtime, it becomes really minimal, right? It doesn't take a lot to run a timer, UART, and interrupt controller virtualizer. So the IMMU is an interesting case because you definitely want to have isolation between the domains, and isolation is definitely very important. Especially, not just isolation for security, but also real-time isolation, meaning that if Linux is running something heavyweight, you don't want to cause any latency increase on the RTOS side, thinking about the obstacle detection use case. So IMMU is definitely important, but even that is not required anymore. Why? Because on ARM, thanks to Bertrand's and his team work, Penny and others have made one-to-one mapping possible and fully featured, meaning that you can define all the memory allocations as well as device assigned to be one-to-one physical and guest physical addresses, so everything is the same. As a consequence, the IOMMU is not needed from translations. Now, you're going to think, wait, what about security and isolation? Yeah, so we target now several different boards from x86 to ARM. We have several different boards on ARM side. All of them have some sort of security mechanism beyond and in addition to the IOMMU. So funnily enough, everyone calls them differently. So there is AXI filters, XMPU, XPPU, TMR regions. They're all different names for the same thing on different boards, which is an address filtering technology. So based on this device is doing this DMA transaction, based on the address, you either block it or allow it. So if you use this together with one-to-one mapping, now you can do isolation without IOMMU. The benefit is the IOMMU is kind of heavyweight from a hardware perspective, and it can become a bottleneck, and not just bandwidth bottleneck, latency too, which is very important. So here is a solution for doing static partitioning without the IOMMU and still have security. On the bottom right here, you see an example of a config file. So DOM0less takes the configuration via device tree, but adding it in by hand is kind of annoying, to be honest, right? It's not the best experience. So that's why we have tooling and scripts to automatically generate the device tree changes for you. And this is all it takes now to add the configuration of 2 VMs, 1 Linux, 1 Zephyr, with device directly assigned and static memory also one-to-one mapped. So the natural extension of this is now everything is one-to-one mapped. It's static partitioning, so now we can run on microcontrollers too. System without an MMU, only an MPU. An MPU is a memory protection unit that does protection on ranges, but doesn't do any translation. So Cortex-R processor from ARM, R52 and R82, supports hypervisor mode, EL2, but they don't support the full translation unit. Xen can run on these. So we do have upstreaming in progress patches for running on both R52 and R82. So Xen does not have any dynamic memory on these systems. It doesn't have any virtual memory either. It's just setting up the MPU, the protection, the separation, and then it's letting the VMs run. So up until now, I talked to you about the simplest case, static partitioning, dividing things up. Now, I'm going to slowly move into more complex cases in the next few slides. Okay, so I want to leave you with some thoughts on how can we improve the simplest of the use cases. So, well, we can go a lot farther into making the simplest case simpler. For instance, we could remove more things from the kconfig. We could make more things underscore init, or pre-configure even more option at build time and providing those data to the hypervisor so that it doesn't have to compute them at boot time. And especially in terms of size, if you calculate the size of the three things that Xen is using at runtime in this configuration, which is a timer, the interrupt controller, and the UART, is only 10K lines of code. So you can go a lot farther toward compiling out or moving things to underscore init to make this use case better. Okay, so as I go into more complex system and the other end of the spectrum, let me talk to you about Xen on AMD x86 with a modern spin. And the next two slides here, I build them honestly, to show you that a modern x86 system and an AMD x86 looks the same as an ARM system. So it's been a little bit, making the diagram on purpose to look alike, but they do look similar now. So why? So on AMD x86 system, taking only PVH. So we have PVH DOM0, all DOM-Us are PVH, so PVH only deployment. And DOM0less is coming to x86. There are Hyperlaunch patches, about to be posted to the mailing list. We are working together with Apertus, Daniel and Christopher on this. So in a system where we have PVH and we have DOM0less on x86, the difference is not that big anymore, right? So if you look at Xen itself as driver for timers, for the interrupt controller, for the MMU, the IOMU, the PCI root complex, remember that with PVH, the PCI root complex goes into Xen, same as ARM. So in terms of drivers and where the virtualization component go, it's the same. Xen runs at a higher privilege level. It's EL2 on ARM and is root mode on x86. But yes, there are significant differences at the hardware level, but from a Xen architecture perspective, it doesn't really matter that much. And we have device sharing technologies, PV drivers, and Virtio. I'm going to go a lot more into details of those, but they work the same on ARM and x86. So they are actually very, very well aligned. So what are the gaps? So like I said, if we take a x86 architecture with PVH only, DOM0less, Hyperlaunch, the PCI root complex moved to Xen, the driver, and as well as the virtualization of the PCI root complex, the architecture looks extremely similar. What are we missing? So, well, first of all, DOM0less, Hyperlaunch is still work in progress. There are patches that are, we got an early version just on Friday. But they're gonna hit Xen Devel very soon. Our aim is to get them upstream this year. PVH domain completion is not quite complete yet. So PCI Passthrough, and there is a series from Stuart pending. ARM and x86 is the same code, but so it's still in progress. It's not quite finished. There are a few little things here and there missing, like suspend resume. I mean S3 suspend resume for PVH is missing. We are also working on Virtio support. What I mean is that in a PVH world, you don't need QEMU, so forget about the old QEMU and all of that. But you might still want to have Virtio devices, which could be QEMU or something else that provide them. It's also, if you are using QEMU, much lighter QEMU, because it's only there to provide individual Virtio devices. We are doing that. We have done the work for ARM at the beginning of the year. And now we are going to make it available for x86 too. So that we are also have this, exactly the same QEMU machine for both. So in year 2025, what's going to be missing? Well, in terms of embedded feature for Xen on x86 compared to ARM. We're going to miss a static one-to-one mapping. We are going to miss cache coloring. In all fairness, cache coloring is also missing upstream on ARM too. There is an in-progress series. This is a technology to isolate the cache in software. It is portable to x86, but we don't have the code to port it to x86 yet. And that's it. So the only other things missing is support for the MMU-less system that they don't exist on x86. So we are, we're going to be extremely close at the end of the year. So now, if you think of a world where on ARM and on x86 too, you have domain construction done by Xen, then, most of the configuration is static, so you don't foresee domains being created later on, then you don't actually need DOM0 anymore. There is no reason for you, it's not true, like you could have DOM0 for monitoring, but let's say there is no reason for you to have DOM0, so you might as well turning it off. And turn it into more like a hardware domain. What I mean is, it's OK to have a domain that by default gets all the hardware. It's not just OK, it's very convenient too. But it doesn't have to have is privileged equal true. So our goal is also shortly, in the next few months, to work on having hardware domain configuration so that you can have DOM0, which is not privileged, or hardware domain, whatever you want to call it, on both ARM and x86. OK, so we looked at the static partitioning configuration. What's the opposite end of the scale, of the spectrum? So the one that is a bit more complex. This is an example of IVI stack based on Xen for automotive. So you see there is a lot more VMs. Instead of maybe 2, you have 4. There is Android, which is pretty complex. You have FreeRTOS, which is an RTOS to run your critical application in, or latency-sensitive application, or Zephyr could be. You have Ubuntu and the Yocto Linux. Yocto Linux is what used to be DOM0, but now it's just the hardware domain. So all of these VMs get started in parallel with DOM0less, so there is no DOM0 VM creation. So that's improved the boot times. So one thing that you should know is automotive manufacturers really care about boot times, because when you turn the car on, user don't want to be waiting for seconds and seconds for the dashboard to come on or to the rear view camera to come on. So they really want the boot time to be the fastest. And this is a critical enabler toward that. All domains PVH. So we are going to have QEMU for providing Virtio devices. But again, this is not the same QEMU at all. We're talking about a much smaller machine that the only thing it does, it provides individual Virtio devices and nothing else. But you see the list of PV drivers and Virtio, compared to static partitioning where you have 0. Here there is quite a bit. You have disk, audio, network, GPU, TE, GPIO, and I2C, right? So there's a lot more virtualized in terms of devices, and the input device is actually emulated right now. So it's just the tablet input device. Now, I guess the next logical question for you is, how does Virtio and PV drivers work in a DOM0less or Hyperlaunch scenario? And I have a lot of slides of that. So I'm going to try to answer that question shortly. Let me start from PV drivers. So PV drivers and Virtio work slightly different in this environment. So PV drivers, so imagine, I'm going to keep calling it DOM0 for simplicity, but it could be the hardware domain, right? So Also, the privilege here is a bit more complicated. So we haven't, not, it's not everything necessarily all figured out yet. But you see that this is one of those cases where the hardware domain DOM0 is not quite. So here, DOM0 is still needed. So you get DOM0 booting in parallel with your DOMU, and then DOM0 simply hot plug any PV devices after DOM0 finished booting. You might say, wait a second, how can the DOMU make any progress if DOM0 is hot plugging the PV devices later? Well, the key here is to boot as far as you can in your DOMUs without having to use PV devices. For instance, you could, at a minimum, be able to boot all of your kernel up until when it's just about to mount your rootfs. And that still parallelizes a lot of the boot. But in an RTOS, you can go a lot farther. Like in an RTOS, you can boot the whole RTOS. I mean, I expect that that's going to be fully booted without having to wait for any PV interfaces. And if you then place your most important things in the RTOS, then you have a pretty solid solution, such as the rear view camera, as an example, or whatever it is that needs to come up in the shortest amount of time when the car turns on. So PV drivers is that way. What about Virtio? So Virtio is this other way. So instead of hot plug, which it would be complex. So keep in mind that whatever solution we come up with, it needs to work for an RTOS. And an RTOS is very, very simple. Basically, there is nothing in there. So how do you get it to work in a way that is simple enough that could be easily implemented in an RTOS? So what we did is actually that was Stuart that came up with the idea. So we have a special flag on the PCI root complex, which is now emulated by Xen. So this is a Xen PCI root complex. A special flag to say, this is, the backend is not ready. How Xen knows if the backend is ready? Because the IORX server, if it's registered or not. So Xen can say, it's not ready, it's not ready, it's not ready, until it becomes ready, and then the flag changes. So the guest can probe and check until the device becomes ready, and keep doing all of the other initialization, all the other inits function in Linux can go on in parallel. I mean, before in parallel with DOM0 and until that flag turns true. What happens if Linux tries to access any of the Virtio devices when the backend is not ready? Well, it's easy, it just gets blocked. So today, what happens if Linux accesses something that needs an IORX server? It waits. It accesses, makes the IORX request. It just waits for the answer. The same here. So again, you are serializing the boot, but it will work. So that's how you get Virtio to work in a DOM0-less or Hyperlaunch configuration. Now, I'm going to talk about Virtio security for a bit and safety. So many of you in the Xen community have been aware of what we consider maybe a weak security model for Virtio, and one of the reasons why we have been favoring PV drivers for a long time. Safety has different words for similar things, but the problem is the same. Safety will call it freedom from interference. So in safety, you want VMs to be free from interference from other VMs. You don't want one VM to cause a crash or even just a delay or latency degradation in another VM. Concept is not the same, but the consequence is similar. Virtio doesn't work, right? So because the trouble is as you all know by now, the Virtio backend needs fully privileged to be able to map and access every memory page of the front end. And you cannot really guarantee freedom from interference if the backend can go in and change any of the memory of the front end. So that's a problem. So how do we solve it in a safety configuration? Well, first of all, in safety, we have one additional thing we can consider. Because we have a distinction between safe VMs, VMs that are running a safety-critical workload, such as displaying the rear view camera, and QM VM. QM, what does it stand for? I don't remember. Quality something. Anyway, unsafe. That's what it is. This is just a virtual machine that's not safe. It's not running something critical. Think of your music playing. on the car. So you could put all of your Virtio backends in a safe VM and all the front end in a QM VM. And then you lose freedom from interference in the direction of the QM VM. Like the QM VM could be interfered by the safe VM. But the safe VM is safe, right? So it's a compromise. But this compromise has issues. This is what many of our many of the proprietary hypervisors do in automotive today. They put all of the backends in the safe OS, and then they have only QM VMs running, such as Linux and Android, on top of the hypervisor. So the downside of this is a pretty significant downside, is that you need to put all your drivers and the backend in the safe OS. Now, the safe OS, by definition, is safe. So it's supposed to be small, run the critical workload. It's also expensive, because it's supposed to be safety certified. So this might work in my example for GPIO. But what about a GPU? Now, a GPU has drivers in terms of millions of lines of code. So now you will be talking about moving a millions of lines of code driver into an RTOS, which will be probably less than a tenth of the size of the GPU driver. So it becomes an isolation and also a code quality problem.
Net on the GPU drivers, at least if you're referring, I think most of the AMD GPU driver in Linux is actually auto-generated header files that are not used by the kernel driver at runtime. Most of that millions of lines of code is in the user space stack. The kernel stack is much smaller.
Right. So bottom line is, wouldn't it be better if we could run those code, user space and kernel space, in a Linux environment where actually has been tested for millions of hours of production usage? It might not be safety certified, but for sure had a lot of better testing than freshly ported code to a different environment. To do that, though, you now need to run the driver and the Virtio backend in your DOM0 or hardware domain now, and run the client in the safe OS, which doesn't work, as we know, because of the privilege. So the first thing I'm going to tell you here is that thanks to Jürgen, that's done the Virtio with grants, we have a solution to that problem. So thanks to the grant table in between, we can run the grant table together with Virtio, taking away the requirement on having the Virtio backend being privileged. So now this scenario, from a privilege perspective, works. So we can have a backend which is not privileged, does not have the right to map and change any of the guest memory, and the front end could be in a safe VM. I'm not telling you, though, that all the problems are solved, right? There are other problems which I listed on this slide, or the next slide. The next slide. There are still other issues with Virtio, such as the fact that when a guest front end accesses certain initial configuration registers to set up the vir queues, it gets blocked on an I or X server request. That's not acceptable from a freedom from interference point of view, because then you're still waiting for the action on another VM. There are other issues, such as the vir queues themselves have indexes that are all on a single page, so there is not quite protection between the indexes. So I'm not saying all solutions are solved, but all problems are solved. That's not true, but we are definitely much closer to a solution than we were before. And I will also say that the biggest of the issue has been solved. And we are actively working, and Edgar in my team is working on finding solution to these other open issues. And Bertan is going to also talk today about other ways to improve Virtio so that this is not a problem any longer. Now, going back to this slide, so you see on the left side an x86 system with the IVI system. On the right side, a Vision Hub system based on ARM with the camera feed, obstacle detection, and Xen is running on both. So in this environment, Xen becomes a little bit like an abstraction layer to make it easier to deploy workload and think about deploying workload in a heterogeneous environment, because it's like the common layer on both sides. So there are a lot of things that we can do here to make things easier for the users, such as maybe listing VMs on both ends, so that you can see what's running on either way. But as a starter, this is what we're working on today. What if you deployed a VM on x86 and you didn't have to worry where the Virtio backend is running? It could be on the local cluster, or it could be on the remote cluster. So this is possible. We are working on a proof of concept, and this is how it works. So the front end normally communicates with the backend, and we want to move the backend to the different cluster. Can I finish? OK. Just 2 minutes. So it could be the backend could be either on the ARM side or the other side. It doesn't matter. The point is it could be either way. And the way we're going to do this is with this proof of concept. We're going to have the front end connect to the sort of a proxy backend on the local cluster. And then the proxy will communicate with the backend on the remote cluster. The idea is that this is only needed for the initial configuration, but the actual data path will be direct between the front end and the backend. We actually want to go here at the end, where the connection is always direct and there is no proxy. But one step at a time, and we are aiming at showing a demo of this proof of concept in just a couple of months. I think this is the end of my presentation, so I want to just remind you, everyone, that we have an amazing team at AMD, and we are now counting also our external collaborator among the top 3 contributors, and actually very close to Susie. There are only 2 commits of difference. I would have loved to. I was trying to move us to the 2nd place, so there are just those 2 commits that get us to the 3rd place in this release. And if you're interested in joining us, reach out to me. We are expanding our team. And in summary, this is the last slide, so time-wise. We have a good way of configuring Xen for static partitioning system. Both ARM and x86. On ARM, one-to-one mapping are even possible, making the IOMMU optional. We have a very good alignment, ARM and x86, with PVH and DOM zeroless or Hyperlaunch. We have ways to run Virtio. We'll soon have ways to run Virtio on a single cluster or also multi-cluster. And we can handle the whole spectrum from the simplest to more complex embedded configuration. And definitely we need to find a common name for DOM zeroless and Hyperlaunch across the 2 architectures, because I cannot keep saying DOM zeroless or Hyperlaunch every single time. And that is the end.